All right, it's 11:15. I think we'll get started. So we're homing in on the end of the semester. Don't forget there are 2 PLAs due today and 2 due on Friday. I had a few extra. I didn't get them up on time. But what the PLAs will do, these 4 PLAs, they won't take you very long. It will help you think about the last week of the material and things like 3D printing, conductive polymers. There's a lecture on biopolymers. And whatever we talk about in class in this last week is fair game for the final. So you can guarantee that there's going to be a couple questions on the final about stuff that we've talked about, like what type of gap is important for semiconducting polymers, and that's a band gap. Or what thermal transitions are important for 3D printing, TG, TM, things like that. And so, you know, they should be relatively painless questions as long as you're paying attention and as long as you're thinking about the material in the last week. So do the PLAs, they'll help you on the final and start to get organized in terms of reviewing all the information, looking at the practice final exam, looking at the previous practice exams, things like that. And this is not a clicker question, just don't forget to fill out the SRTEs. All right, so you should be pretty set on where you stand in the class. So this is all in the syllabus, but here is the grading guide just to make sure that we've talked about it. And so there's no curve. I will round up. So if you have a 93.5, that will get rounded to a 94. So don't worry about that. If you have a 93.1, there's no guarantee unless, you know, I can see something in your grades that shows you're improving or you did something, you know, to help you with that bump. But I generally try and give you the benefit of the doubt. So make sure all your homeworks are in. Make sure that you've taken care of all your exams. If there's a grade missing, let me know. Stuff happens. And the final exam is 20% and the final is cumulative. All right. So for the resident section, which you all are, if you have an R in your section name. So for PLAs, above 75% gives you full credit. So don't worry about missing 1 PLA here or 1 PLA there. So anything above 75% and you're set, full credit. Everything above 50%, you get 80% credit. And so, you know, I don't expect you to get every little single point on the PLAs, but good effort will get you most of the points available. And then if you're below 50% in the PLAs, you get the percent earned out of the total. So if you got a 40%, that's what you're getting. And PLAs are 4% of your grade. We don't have Zoom chat, but clicker questions are 3% of your total grade. If you have above 75% participation in clickers, there's 32 lectures that I ask clicker questions in. And so I just updated the scores. And so out of 32 possible clicker sessions that we had, above 75%, you get full credit. So you get the full 3%. Above 50% participation in the clicker questions, you get 80% credit or 2.4% out of 3%. Below 50%, you get the percent earned. Now, I tried when I updated the clickers, I tried to get all the excused absences in there. So everyone should be pretty up to date. And I think 24 points out of 32 is that 75% magic number. But if you look, and if you're at 23 or 22 or something, or you had an excused absence for whatever reason, and you told me in class, but you didn't send me an email, there's no guarantee that I mark that down in my notes. And so if you're close, well, if you're above 75% on the clickers, we don't need to talk. You're all good, even if you have excused absences. But if you're near 75% or near 50%, just let me know by email in Canvas. You know, that's the email that I'm looking at when I look at this course. If you just sent me a regular old email, there's no guarantee that I can find it. So if you think that you're getting shorted on the clicker, send me a Canvas email through the course, and then I will definitely see it. I'll take a look at it and I'll update you. But I think I got a lot of the excused ones, especially for sports travel, illness, things like that. But let me know. All right. Any questions on grades? Any questions on how I'm going to figure stuff out at the end of the semester? Remember, Canvas doesn't give you the full picture because Canvas doesn't know how to drop any grades. Canvas is not perfect in the percents. And so when you look at the Canvas percents, they're not going to be great. You just need to do it by hand, make up a little spreadsheet. Yes?
So I forgot, for MATSE majors, do you just need a C or a C plus for the class B pass?
I think it's a straight C. Yeah. So for MATSE majors, this is a required class and you need a straight C or better. There is no such thing as a C minus, but yeah, C or better. Yes.
When did you say that you would drop our lowest test grade against?
On Saturday after finals week. So I sit down and I have a little spreadsheet. I don't trust Canvas either. And I put in all your grades. And then on Saturday morning, I manually drop the lowest one. You should know what that is right now, because you can add up the, I think every exam was 20 points in multiple choice plus 6 points. So you can figure out which one to drop right now. So that's why Canvas is not accurate, because it doesn't know how to drop grades. It doesn't know that if you're above 75% in iClickers, I'm going to give you full credit. Canvas won't do that, doesn't know how to do that. And so make sure that you get out your Excel spreadsheet and type everything in. And then if you want to do a check-in, you know, what I'm looking for is, I think this is my grade in the class and this is why. And then you can ask me what I think. I don't want an email saying, what is my grade going into the final? You know, I want you to do some work first and check it with me. And I'm happy to do that. But just don't send me an email and say, what is my grade? Because I won't know until Saturday. But send me an email through Canvas. If it's not through Canvas, I can't guarantee that I can help you because I just might not see it. Any questions or comments? Okay. Don't forget about the SRTE. It helps the next class coming. I change the course every year. And so if you really love something, we could do more of that. If you really hated something, we could do more of that. And I don't see the SRTEs until like 2 or 3 weeks after the semester. So it has absolutely no bearing on what happens here. All right, any questions on conductive polymers or any questions on 3D printing polymers before we go forward today? Okay, I should mention one thing, hold on OneDrive. We're in section 5, and I think we're gonna get all the way through 3D printing polymers. These are all the PowerPoints. We just talked about conducting polymers. We talked about smart polymers. You had a PLA on that. I don't know that we're going to get to biopolymers. And so if we don't talk about something in class, it's not going to be on the final, especially in the last section. But if you're interested in biopolymers, you can check out that PowerPoint. You can ask me questions on Friday. We can pull up some slides. I mostly want to talk about reviewing for the final on Friday, which is this PowerPoint right here. And so you should check out PowerPoints 38 and 39 before the lecture on Friday, because Friday will be the last time you have a chance to ask a question when we're all together, but there are office hours coming up. I have office hours, I think, today, Thursday, Friday, Monday, Tuesday. So you have plenty of chances for office hours, or you can make an appointment or shoot me an email. All right, but make sure you're up on the PowerPoint slides. Any questions? All right, and you all know when the final is, so we don't have to talk about that. All right, so the question is, I mean, so 3D printing and additive manufacturing are the same thing. So, oh, if I can draw, or 3D printing. And the big idea here is that, has anyone ever seen a CNC mill or a lathe or something like that? Yeah, and so what a CNC mill or a lathe or a water jet cutter or something like that does is basically takes a block of material or some sort of stock, whether this is Ultem polyamide or whether it's aluminum or steel, and it does some sort of machining, or in this parlance, subtractive manufacturing. So you take away material in order to get whatever object you want. That's fine. That's been done for a long time. Machinists are very good at what they do. They have computer controlled CNC machines and all sorts of things now. So you can make some really awesome stuff. But one of the big things is that you get waste from that, because you take something that started as a solid block of material, and depending on what part you want to make, you do have some waste. Now, waste can be recycled. It's really important to recycle metals. We're working on recycling polymers and other things like that. The other issue with subtractive manufacturing is that there's some objects that you just can't make solid. So if you've worked in a mechanical design lab, or you've worked in a internship where they're making products, sometimes they have to take two parts that are machined separately and either join them, weld them, glue them together. A lot of plastic parts have a weld line in it that you can see. That's where they had to put those parts together, because they couldn't machine or manufacture that part in one solid geometry altogether. But the promise of additive manufacturing is that you start with your raw material, and it can be a polymer powder, it could be one of those filaments, it could be something like that, and you can build a 3D object from the ground up with minimal waste. And you can build things in additive that can't be traditionally made. And that's really interesting, because if you take a class on additive manufacturing and you really get into the nitty-gritty details, decreasing part count is a big deal. Decreasing assembly time is a big deal. And so all of those things are good in terms of additive manufacturing, and that's why folks are interested in it. Now, 10 years ago, or even 5 years ago, most people were like, well, 3D printing, additive manufacturing, whatever, it's not that interesting. But today, we get a lot of calls from industry looking for folks who know how to do additive manufacturing, because the conversation goes something like, we know additive manufacturing is important. We don't have a lot of people that know a lot about it, but we're trying to get into it because we know it's coming in terms of a new way of manufacturing our products. And so lots of companies are interested in exploring additive manufacturing, and it's really here to stay for the foreseeable future. All right, and so we just talked about pros and cons. So the one cool thing with pros is that it's completely customizable. So does anyone know what injection molding is? Yeah, so injection molding, you take some melted polymer and you inject it into a steel mold, and you get a toothbrush, or you get, this half of this remote control. But in order to make a different type of toothbrush, or a different type of injection molded clamshell for this remote control, you need a new mold. And those molds are really expensive, like $75,000 for a stainless steel cavity that you inject polymer into, because it has to be precise and it has to withstand the pressure. But with 3D printing, all you do is change the computer program that controls this printer, and you can get a new product. So there's no tooling, or there's no mold making or anything that's needed. And that's a big advantage, especially in polymer additive manufacturing. The biggest con of additive manufacturing, or the biggest drawback, is that it's slow. If you've looked at the MakerBot that you used in high school, or if you look at your Ander printer that you have at home or in your apartment, you're basically watching the thing and it's writing just teeny little lines of polymer one at a time. Versus in injection molding toothbrushes, you can injection mold like 10 toothbrushes in 5 seconds. And then you can injection mold another 10 toothbrushes in the next 5 seconds. And so this issue of there are pros and cons of additive manufacturing, you really need to think about, why are you going to additive manufacture something, and when does it make sense? So why choose additive, and when does it make sense? So if you only want to build 5 things, additive is probably a pretty good way to go, right? It's easy to print 5 objects over a day or so. If you want to build 100,000 things that are all exactly the same, additive manufacturing is probably not the way you want to go, because you can injection mold that or do some other sort of traditional manufacturing process. I will tell you that there's some really cool, if you're interested in this, there's some really cool case studies on Invisalign. If you've ever seen a pair of Invisaligns that have those little striations across them. So Invisaligns themselves are not 3D printed, but the molds to make Invisaligns are thermoforms, so those clear braces. They 3D print the molds of your mouth and where you want your teeth to go, and then they thermoform this plastic on top of those molds. And those molds have those little striations in them, and that's why Invisaligns had those little lines in them. So there's a really awesome video on this. We'll watch it if we can. And hearing aids. If you've ever bought a hearing aid, they're really expensive, like $3,000 or $5,000. And 95% of the hearing aids that are made in the world are made using 3D printing. And some of the big hearing aid companies have 3D printing factories in order to crank these things out. And each Invisalign and each hearing aid is made for an individual person. So every single Invisalign part and every single hearing aid part is custom made. And so that's why they use additive manufacturing at large scale to do these. And I'll show you some videos if we have time, but they're really interesting. All right, so if you've never seen 3D printing, here is the basics. Oh, assuming this video works. So this is one of the cons of additive manufacturing. It's just really slow, right? You can only deposit a couple grams of polymers at a time, but you can build up whatever shape you want in terms of these computer-generated slices. And we'll just watch this a little bit longer. And there's no way to injection mold something like this. This is difficult to machine. And so, especially for intricate parts like they're building up here, I think this is the Colosseum in Rome. This is a good way of the model of the Colosseum. Great. All right. That type of 3D printing. We're going to talk about some other type of 3D printing in a second. And so what's cool about 3D printing is that you can buy 3D printers off of Amazon, and you can also have professional 3D printers. And places like automotive companies are doing a lot of 3D printing. General Electric is doing a lot of 3D printing. You know, there's some, they've 3D printed a car as well. There's some real engineering horsepower that's going into additive manufacturing and new types of processes. And polymers play a really important role in that. So it turns out that once additive manufacturing has started to take off, we really need to get our terminology straight in terms of what types of processes that we're going about in terms of our additive manufacturing. And of course, there's a similar diagram for metals, ceramics, etc. So the way that ASTM classifies part of polymer additive manufacturing is called thermal reaction bonding. I don't know why they call it a thermal reaction. It's just thermal bonding. But what sort of polymer properties are you interested in if you're interested in thermal processing of polymers? TG, TM, viscosity, modulus is a function of temperature. So let's insert a new slide here. So for thermal, we've got TG, TM, we have modulus versus temperature or viscosity. What other things happen when we thermally process polymer? What about all the way back when we talked about how TG and TM are defined? How do we measure TG and TM in one instance? Remember specific volume versus temperature? What happens when you heat up and cool down polymers and they go through these thermal transitions? They expand and contract, right? So you have volume change. Versus temperature. So volume change versus temperature might be really important because if you want high precision 3D printing and you're heating up a polymer and cooling it down, the CTE might be really important. And you could get built-in stresses in the polymer because of that. And we have crystallization. Are crystallized polymers in general higher or lower modulus than amorphous polymers? Higher, right? And so we want to try and promote crystallization in 3D printing. And so we have to think about that in terms of the thermal history. What's the TC? How is that? How long are we crystallizing the polymer? Things like that. So these are some of the fundamentals that play into this idea of thermal reaction bonding. And for additive manufacturing, you've all seen probably filaments, melted material. This is pellets or something like that. So like an extruder. And if you want to do powder bed fusion, you might use polymer powders. And so if you go a little bit further, you've got deposition nozzle, just like we see on a MakerBot. You might have a extrusion print head or a powder bed. And so then we start to get down to material extrusion additive manufacturing. We can talk about material jetting, although that's not that common in the thermal regime, and then powder bed fusion. And so this gives us a guide now how to connect the properties or the thermal properties of a polymer down to whatever process we're interested in. The other branch of polymer additive manufacturing is called chemical reaction bonding. This is the terminology they use, but what it really means is polymerization. And so in this process, we're going to go from a liquid polymer, sometimes called a resin, and it's going to be a light reactive photopolymer cure, and that's either done in what's called a polyjet, we won't talk too much about that, or vat photopolymerization. So what type of polymer reactions have we seen that are really fast that we might be able to use to do this 3D printing? Which type of polymer reaction do we build molecular weight with quickly, and so we get high molecular weight in a fast time? Yes. Radical. Free radical or chain growth polymerization. So for chemical reaction, We need fast polymerization, which in general is going to be chain growth, free radical. So in thermal, what happens is you start with the solid polymer, you heat it up so it flows, then you cool it back down and it's your set 3D part. In chemical reaction bonding, you start with the liquid polymer and you shine light on it to cause this chain growth polymerization, and then you get a solid polymer very quickly. And that happens because the first plot that we have to look at is as a function of conversion. We have molecular weight. And so for chain growth, we get molecular weight building quickly in that case. And you can fill in living and step on this plot. Don't forget how to do that. We've talked about that plot a lot. The other plot that's really important is that if we plot the glass transition temperature versus a molecular weight, we get a fast increase in TG, and then we get a leveling. So this is the plateau, molecular weight, and we get whatever TG of the polymer we're interested in. And so what's cool about this photo-induced free radical polymerization is that things that have TGs below room temperature are liquids. And as the TG comes up above room temperature, it's going to be solid. And so it's this combination of fast buildup of molecular weight using chain growth polymerization and rapidly increasing the glass transition temperature, because you're rapidly increasing the molecular weight, that allows you to cross this liquid solid boundary. And that's a big idea in terms of putting together these concepts to make light reactive photopolymer curing a reality. So the same thing happens when you get a filling and they put that blue light in your mouth. That's light reactive photopolymer curing, and the filling material goes from a paste or liquid-like to solid within just a couple seconds. Same thing happens with stereolithography, is you build up molecular weight quickly and you get a solid polymer from a liquid precursor. Any questions on this? I'll show you some videos of this process in a second, but I wanted to compare and contrast the two ways to process polymers. So it's going to be important for you to know what are the fundamentals of thermal processing polymers versus what are some of the things that you need to know for chemically processing polymers and additive. All right, so a lot of you have done fused filament fabrication, or this is also called FDM, MakerBot printing, etc. So this is our raw material in our filament spool. You heat it up and you can build a solid object just like a 3D printing pen or something where you draw out your part. And it used to be that fused filament fabrication was like, well, you know, it's just used in schools. It's sort of a hobbyist thing, but a lot of companies are using fused filament fabrication for jigs and fixtures, for other sorts of tooling, because it's fast, it's inexpensive, and you can get strong thermoplastic properties from this process. A lot of the commonly used polymers in this process are PLA, which most of you have probably used. What type of polymer is PLA in terms of the base chemistry of the polymer, if we had to name it? So it's glassy, it has a high TG, but what's the chemistry? Yeah, it's an ester, yeah. Polyester. It's called polylactic acid because it's a condensation product of lactic acid, but because it's got this ester group, it's a polyester. Here is polycarbonate. So here is the carbonate group right there. Remember, we can slide those parentheses however we want. And so the carbonate group is oxygen, carbonyl, oxygen. That's a carbonate group. That's in your chemistry review with ester, amide, all the rest. And then ABS is unimaginatively named because it stands for acrylonitrile, butadiene, and styrene. That's in ABS. How is ABS made? So if we take these monomers and we want to make a polymer out of them, what type of polymerization might we use? Step growth or chain growth? What form do these monomers have? Or what functionality does acrylonitrile, butadiene, and styrene share? Yep, they're all chain growth monomers, right? So this is chain growth. ABS is made in a special way, but they all have double bonds that we can use for chain growth. What's the degree of functionality of butadiene if we have 1,4-butadiene? 2, right? And so remember, this is a diene. So we can have 1,2 or 1,4 addition. And if we have a functionalized diene, of course, like isoprene, we can have 3,4 addition there as well, but butadiene is symmetric. So some of these basic fundamentals that we talked about in terms of what these polymers are show up right in additive manufacturing. And you should be able to tell me, if I give you the monomer styrene, you should be able to tell me what its degree of functionality is, how it might be polymerized, chain growth or step growth, and some other interesting things about it. All right. Any questions so far? Any comments? So what I'm trying to do is remind you of some of the important things that I'm going to ask you on the final in terms of fundamentals, while connecting those to something that's interesting like additive manufacturing. So we've already talked about temperatures. What if, so because we're forcing this polymer out of this nozzle, what if we're getting too much dripping? I don't know if you've ever done any 3D printing and the polymer's just coming out, it's hard to control. What might we do to the temperature of that heater if the polymer is just leaking out of there? We're not getting good resolution. Yes? Lower it. Why should we lower the temperature to stop the polymer from dripping out? What fundamental property are we accessing? It's not creep because it's not really solid. But if we look at the modulus versus temperature, remember we have glassy, here's the TG, and then we have a roll off out here at high temp. This is liquid. This is rubbery. This is glassy. And so modulus, when it's flowing, is called viscosity. And so if we back off on the temperature, the modulus of the polymer goes up a little bit. And so effectively, it won't creep, or we don't get stress relaxation as fast if we decrease the temperature. Good. And of course, if we're not getting enough material flowing out of the heater, we turn the temperature up because we want to decrease the viscosity or make the polymer more liquid-like in order to get it to come out of that nozzle. Can we do thermosets in general, or can we process thermosets in general using this FFF scheme? No, why not? Well, that's not the exact reason why. Why can't we process thermosets under this regime? They can't be deformed by heat. very easily, right? They have cross links. And so we know that thermosets or cross-linked polymers have a very long rubbery plateau, right? And so we can't thermally process them. And so in general, we're going to use thermoplastics. For this type of 3D printing. And so depending on how we build the polymer, we can get different orientations of these roads, we call them, in the polymer. Great. And this is not a clicker question. This is just an FYI because I'm not updating the clickers anymore. And so if we think about this polymer that we just built, and if we build the polymer with roads going this way, versus if we build this part with roads going this way. Oh, let me erase that. Road orientation. And we think about this idea of the elastic modulus of the material. In one case, when we pull this tensile bar, we're going to be pulling along the direction of the roads. And in the other case, we're going to be pulling across the direction of the roads. And when we pull along, we get a higher tensile strength because we're pulling on those filaments versus pulling crosswise to those filaments. And we talk a lot about that in our 3D printing classes that you can take at the 400 level if you want. So this is just a schematic of that. And so if you look at the tensile strain and the strain at break as a function of orientation, you notice that there's this interesting orientation effect because of the anisotropic material properties based on how it's printed. All right. So the other interesting thing that you need to think about for additive manufacturing is that you don't need to build everything just standing up, right? Okay, I'm going to build this traffic cone. I just might as well build this thing standing up. But if you want to make an intricate part like this lion, or if you want to build something that has a high aspect ratio in this direction, you need these support structures. Has anyone ever used support in 3D printing? So what do you do with the support after you print it? You can break it off, that's right, if the support is thermoplastic. Has anyone ever used a dissolvable support? Yeah, what polymer was that dissolvable support? It's a water-soluble polymer, right, that you can still 3D print, and that's polyvinyl alcohol. So this is a semi-crystalline polymer that you can print in just a garden variety 3D printer. And so you can use, and it's white or translucent, you can use this polyvinyl alcohol and dissolve it in water and then get your unsupported thermoplastic part. And so we've talked a little bit about polyvinyl alcohol, but this is worth remembering that it's a water-soluble glassy polymer that can be used as a support material and washed away after 3D printing. Any questions on that? Yes?
What then happens to the polyvinyl alcohol in the solution?
You can either take away all the water and recycle the PVA, or you can dispose of the PVA, in some sort of safe manner. Yeah, it's a benign polymer. Turns out there's lots of polyvinyl alcohol in food, in cosmetics, and other things like that. And so it's not too bad of a polymer, but it is dissolved in the water. You have to do something with that. Don't put it down the drain because that's what causes problems with plumbing. All right. Any other questions? Any other comments on thermal bonding of polymers for additive manufacturing? All right. So I want to talk a little bit about chemical reaction bonding, and especially I want to talk about vat photopolymerization. This is also known as SLA or stereolithography. And so this is photo-induced free radical polymerization. And so we've studied this already. And the way that it works is that you use light. So either from a scanning laser in top-down stereolithography, this is a liquid pool where you solidify solid layers of resin, or you shine light from the bottom through a transparent window, and you get solid polymer formed on this build stage and it's pulled up. So this is really interesting. It's a little bit more expensive polymer, an expensive printer than your FDM, but it uses these concepts of photo-induced chain growth polymerization in order to make this work. And the basic process is this. So benzoyl peroxide is a photoinitiator. And you get two radicals that are eventually going to turn into the initiator. For photo-induced free radical polymerization. Does anyone know what type of group this is called? Right here. Double bond with the methyl group connected to the ester. What did we call that type of group when we studied free radical polymerization? This is a methacrylate, right? So it's a methacrylate because there's a methyl group right here. This is the double bond that polymerizes, and then this allows that polymerization to happen. And so the photoinitiator starts, this is the second stage of initiation formally, starts this chain reaction. So you shine light in order to get initiation, you get free radicals, and then you get very fast polymerization chain growth. And as we said before, you get a very fast, right here, a very fast buildup in molecular weight from this process, and that is accompanied by a very fast increase in the glass transition temperature. Because the only difference between a solid polymer and a liquid polymer is higher molecular weight generally for a solid polymer, and the glass transition temperature has to be high for it to be a solid at room temperature. So all you're doing is going from small molecules, low molecular weight, to high molecular weight, really quickly, within half a second, or 200 milliseconds, or a couple seconds if you have a potentially slow photopolymerization. And it turns out there's lots of different types of monomers to use. So this is an acrylate. In fact, it's a diacrylate, and you've seen PEG diacrylate before. This is a crosslinker. What's the DF of this crosslinker right here? Six, good answer. 2 for each double bond, or 2 for each acrylates, because we don't count this double bond. We never polymerize across carbonyl. So 2, 4, 6. Great. DF of 1 right here for butyl acrylate. What's the DF of this dimethacrylate right here? There's only a methacrylate on each end. So what would the DF be? 4, 1 on each end, right? Each of these is DF equals 2 because in this generic vinyl type monomer, remember DF equals 2 because we're going to connect the chain this way and we're going to connect the chain that way. Okay. Any questions or comments on this? So it turns out that stereolithography was really the first type of additive manufacturing invented widely. And this used to be called rapid prototyping. And so Chuck Hull, who started 3D Systems, who's still alive, who you can go see at additive manufacturing meetings, started this idea of stereolithography, and he's really one of the pioneers of this field. And so what this does is this is just a colorized schematic from his original patent, is that you have liquid resin in this vat, you shine a laser on top, and so you get a fast liquid to solid transition. And you make your part by building up layer by layer, just like a MakerBot, only it's happening at a liquid air interface. Let's see. I do have a good video of this. I don't have a good video. We'll watch some 3D printing videos next time, maybe. And so what's interesting is that there's lots of ways to do this. And so you can use a galvanometer, which is a moving mirror that steers a laser. There's also DMD, which is called a digital mirror device. And DMDs are what's in a digital light projection TV or a DLP computer projector like that. So there's a DMD in there making this image. And it turns out that you can use a computer projector to do 3D printing if you want, by just printing light or just making light and dark PowerPoint slides. And you can build up shapes really easily using this idea. And this is exactly what we do in my lab when we're testing a resin, is we project different PowerPoint slides and we cure different shapes using unreacted resin or a liquid resin and turn it into a solid. Okay. Let's see. The last thing I want to talk about is, so we won't talk too much about multi-photon adsorption, but the last thing I want to talk about is that we can make really new types of constructions using this thing called a nanoscribe. So it's basically just a really small 3D printer, or a small, it's a regular sized machine, but it has a small 3D printer inside of it. And this is an interesting video, so let me show this to you. There we go. I'm sure it's got some good YouTube music. Oh, hold on. So what they're doing with this printer is doing microfabrication. So this scale bar right here is 400 microns, which is really small. That's like 4 human hairs. So what they're interested now is they're using an SEM to image these things, because you can't see them optically. They just look like a little speck on the glass slide. But now instead of making a Pentium chip where you're doing 2-dimensional layers all the time and stacking them on top of one another, now you can start to make 3D constructions at this really, really small scale. And this is cool because, you know, we sort of get the idea of building large-scale manufactured objects using 3D printing, but now we can really scale that down. All right, so you can check that out later. And so I just have one more slide, or 2 more slides. So you can take something that's built in large scale and you could scale it down with really good resolution. So the last thing that people are thinking about in terms of 3D printing is, what if you can get the 3D printing object to change shape? So what is a polymer that's just sitting there, and then all of a sudden you shine a stimulus on it and it changes shape? What do we call that on Friday? A smart material. And so now people have worked to integrate smart materials into additive manufacturing and do all sorts of cool things. So here's our orchid that folded itself. This is a shape-changing hydrogel, and this is a soft robotic arm, or a box that folds and unfolds depending on the stimulus. And so now, depending on the polymer function that we build in to our additively manufactured objects, now you can have 3D printed smart materials to do cool stuff. And that's where we're headed. All right, that's all I have today. I will see you on Friday.